I know. It's so disgusting. I need to speak my own information with her husband because I bet it's based on that. And if I find out her husband's a childhood friend with us.
Okay, if we can turn to page 7 in your packet. Hopefully, you guys had a chance to join in on the classes or watch the videos. I recorded we had 2 lessons online. One finished talking about average value theorem, second fundamental theorem. And then more recently, yesterday was talking about use substitution. So I'm going to kind of run through the steps again. If you hadn't had a chance to watch those videos or can join the class, hopefully you guys can catch up tomorrow or over the weekend, since we are closing in on finishing this unit. And we'll start our test review next week. Okay, and now I should be able to give back your quizzes by next Monday as well. Okay. So we talked about how use substitution is a way for us to handle problems that are more complicated than the trig or power rule that we have available. And for the more complicated problem, we're basically having to undo something that was coming from chain rule from derivative. So kind of putting everything back together when something has already gone through chain rule can feel complicated. So what we do is we identify a temporary variable, a variable u, that can kind of help us create an easier version of the problem, solve that easier version, and then bring back our original variable. So a quick review, for example 2, the way we approach this problem is we first ask ourselves, for every integral problem, we should always ask ourselves, can I just get by with expanding and relying on power rule? And if that doesn't, either it's impossible to do, or it's too messy to go through that process, then we can go through and think about use substitution. But we should always ask ourselves, can we just rely on expansion? So for example 2, we could expand, but that 15th power means you got to write your binomial out 15 times, and you're not going to be expected to do that. So a much more efficient way is let's create an easier version using use substitution. So the way that I'm having us identify our u value is starting with what's inside the parentheses. Okay, if you can find a set of parentheses, 90% of the time, that's going to be where your u value is. We do have some exceptions, but we'll talk about those exceptions once we are more comfortable with like the easier versions of these problems. So our u value is going to be the x squared plus 1, the expression inside the parentheses. And our first goal is we're going to underline the x squared plus 1 in the dx. Okay, those are the pieces that we want to replace first. Anything that's not part of this, we're just going to recopy into our problem. Okay, so our u value is x squared plus 1. And once we find our u value, we're always finding the derivative after that. So du over dx, because we're asking for the derivative of u with respect to our independent variable x, and the x squared plus 1 becomes 2x. Right? Now that we have our derivative, we're going to cross multiply, okay, and then we're going to solve for dx. So if I cross multiply, I get 2x dx equals du, dx equals du over 2x, and then I make my substitution. Replace the underlying piece with u, replace the dx with du over 2x, And when we do that, we're kind of piece by piece bringing everything back in terms of u. And we need the x's to cancel out. If the x's don't cancel out, we're kind of stuck in that cleanup stage until the x's can go away. In this case, though, the x's do go away. X in the numerator, x in the denominator, they cancel out, great. But there is a leftover 2. It's okay to have a leftover numeric value, just to make sure we keep track of it. So I can push that 2 out in front as 1/2. And now I have a power rule for me available to use, right? Because we have a rule that matches exactly with what we want to use. U to the 15th power, we can go through power rule. The 1/2 is the coefficient that just hangs out in front. So we get u to the 16th over 16th plus c. U is only a temporary variable. So we want to bring back our original variable. I'm going to pull that 1 over 32 out in front and then replace the u back in terms of x. And this is now my antiderivative. And then the rest of the lesson yesterday, we just went through different variations of that. We tried to expand. If we couldn't expand, then we try to create the set of parentheses so we can pull the u value out. And then with u substitution, our goal is to create an easier version of the problem, solve that problem, and then bring back our original variable. Okay, let's go to page 8. So just briefly, we also talked about problems like example 5, where we don't have a rule that can handle this mess of an expression, but we could create 2 sets of parentheses, right? And that at least gave us some options to determine which could be the u value. And then only one of them is going to work. So after we identify a potential u value, we always want to think about the derivative. And we're always trying to find, is there a match for the derivative in the problem? If there is a match, then that typically is a good way for us to know that we're probably going to go down the right path if we did that. Example 6 is an example where we do see a set of parentheses, but this can be solved using power rule expansion. So this is a reminder that our first option for any integral problem is always, can I just get by with expanding power rule, right? Can I get by with the skills that we knew from the quiz? And if we can, we need to solve it that way, because u substitution is not a process that can handle every situation, right? And if we're stuck in thinking that u substitution is our first step, then it's going to be very hard for us to backtrack and think, oh, wait, maybe it's power rule expansion. I think usually what happens is students are going to force a u substitution, and then they're going to create, create some algebraic step that is not correct, and then try to get down to their answer, rather than thinking about that there's an option other than u substitution. So always want to consider expansion first. We should always be able to look at the problem and say, okay, can I rely on just expanding without having to do a whole lot of steps, right? We should be able to look at a problem and be able to recognize, okay, I can do this with power rule versus I can't do it with power rule. Example 7 was one of those problems where our u value was x plus 3, but the derivative did not quite get the x to go away. And because it didn't quite get to go away, we have to resolve this x before we can do anything with antiderivative. So we have to find a kind of like a clever way to get that x to be replaced. And our way of manipulating is rearranging this equation that we assigned at the beginning. Because u equals x plus 3, we can rearrange this and say, well, then x equals u minus 3. And if I can rearrange it to solve for x, I can replace the x in our problem in terms of u. And once everything is in terms of u, I can algebraically get it to a point where I can rely on power rule. And then once I apply power rule, I can bring my original variable back. All right, let's try example 8, where we have to go through another potential change of variable here. Okay, first things first, we always ask ourselves, can I just rely on expansion and power rule? Order of operation prevents us from doing that, right? I can't distribute the x squared through. We're kind of stuck. Power rule is not going to be able to get us where we want to go. So our next step is, well, maybe use substitution is our next option. So let's get some parentheses to show up, so we can at least have some options for our potential u value. We know we can rewrite that radical. And now we want to pick out the u value. Our u value is typically going to be what's inside the parentheses. So we're going to target that as our u value. So always underline what's inside the parentheses and the dx. And that is a reminder that those are the two pieces you're going to replace first. Okay, don't replace anything else. Just replace those two, and then we can take a step back and decide what our next step is going to be. Okay, so our u value is 2 minus x. Our derivative, we're always going to do du over dx. The 2 goes away, the negative x becomes negative 1. Cross multiply. Solve for dx. If I divide both sides by -1, that's the same thing as multiplying by -1. So dx equals -1 du. Right? I can say du over -1, but it's just a little bit cleaner to just write it as -1 du. Dividing it by -1 is the same thing as multiplying by -1. Okay, so now I have enough information to substitute those two pieces. The x squared is going to stay. We don't know what to do with that x squared just yet, so we'll keep that. Parentheses gets replaced with u, and dx gets replaced with -1 du. Now, we would like, we know we can't move forward unless the x and the u are resolved, or basically the x has to be resolved. I see a lot of students do this. They will say, oh, power rule for x squared, power rule for u, and then plus c, and I'm done. So we can't do that because these are being multiplied. And we have to, if we're going to use substitution, the x has to find a way to be removed. So the way we remove it, or the way we rearrange it, is we need to find something that is equivalent to x, but not in terms of x. So the way to do that is we're going to go to our assigned equation between u and x and rearrange it to find a replacement for x. So if I rearrange this equation, I can get it to be x equals 2 minus u. So now this is my replacement for the x. So our first so our first hurdle has been, we've cleared it, right? It's just trying to get that x to be replaced in terms of u. We're still not ready to find the antiderivative. There's still quite a bit of algebraic cleanup, but at least there's a way to do it, right? Before, we couldn't expand, distribute through, but now there's a way to do it. We can FOIL this out, distribute that u to the 1/2 through, get everything nice and separated, and then do power rule for each one of our terms. Right. But before we do that, I'm going to rearrange it in a way that I can limit the amount of expansion I have to do. So I'm going to pull the -1 and u to the 1/2 in front. And my next step is I'm going to FOIL and expand out this set of parentheses, and then I'll distribute the -u through. So the result of the 2 minus u times 2 minus u, I always want to, we always want to remind ourselves to write it out twice. We don't want to just distribute that 2 through, right? We're missing something if we did that. So write it out twice and convince yourselves that you're expanding each of the terms. So I get 4. The middle terms is minus 2u and minus 2u, which is minus 4u, and then plus u squared. Okay. We're getting closer to getting ready for power rule, but we still have to distribute through. So let's distribute the -u to the 1/2 through. If I'm multiplying the u variable, I'm adding exponents. There's a hidden 1 above here. So 1 plus 1/2 is 3/2. And then 2 plus 1/2 is 4/2 plus 1/2, which is 5/2. Okay. Now we're ready for power rule. Took all these steps to get to the point where we can now do the calculus process. Okay, so now that we're going to apply power rule, the next step will allow us to remove our notations. Okay, let's flip all those fractional denominator to the top. So as I clean up, I'm also going to replace the u back in terms of my original variable. Keep in mind, the u variable is to help us with an easier problem to solve. But once we solve it, once we find the antiderivative, just keep in mind our u variable is only a temporary variable. It's not going to be in our final answer. So today's lesson, we're just going to go one step further after this. The one step further is, what if there were bounds involved? If there were bounds involved in this problem, we're going to go through the exact same steps as before, but instead of a plus C, we'll do a half bracket with the upper and lower bound and then plug in accordingly. Right? So a lot of what we do today will just feel like review, but then with the final steps will just be a little bit more because we have to involve the bounds. Okay, page 9. We have to keep reminding ourselves that the bounds, even though it's the first thing that we see, because we read from left to right, it's the first value we see, but it's the last thing we do. Okay, a lot of students want to do this. They want to just plug the 1 and 2 directly into the expression. The 1 and 2 is the bounds for the antiderivative, not for the integrand, not for the expression you see in front of you. So to help remind us of that, what we can do is just remove the bounds and just force ourselves to just look at the problem without the bounds. This is not going to play a role until the very end. So I'm going to solve the problem without the bounds. First things first, can we expand? We could, but that 3 is a little high. So we want to explore U substitution. Our U value is going to be what we see inside the parentheses. Next step, du over dx. Derivative is simply 2x. I like to put a 1 beneath because my next step is to cross multiply and move towards solving for dx. Solve for dx. So now we have enough information to substitute the pieces that we've underlined. Things that we did not underline, we're going to have to make sure we bring back into our problem. Okay, we don't want to make any changes to it. We don't want to lose those terms. U to the third, and dx is replaced with du over 2x. Now we can't proceed with our calculus step unless the x's are gone. It's okay to have leftover number coefficients. It's not okay to have leftover x's. But in this case, looks like both the variable and the coefficients go away. So that makes it less things to keep track of. But the big key here is the x's have to go away. It just so happens the coefficients also go away as well. So we're left with integral of u cubed. This is nice. This is just a nice power rule problem. So we go ahead and apply power rule. Becomes u to the 4th over 4. I'm going to make 2 columns here. I want to show 2 different ways of evaluating the bounds. So let me do method 1 here. This is the method that I think most of us will prefer. It feels more straightforward. But I also need to show you method 2 because sometimes the AP exams on their multiple choice section, they would work it out using method 2, and we need to be able to at least know um, how to resolve those types of forms. So the first method is we want to bring back the x, right? The way that we would do this problem without the bounds, we would still bring back the x and we'll do a plus c. So the u gets replaced with x. I'm going to pull the 1/4 out. So replace the u back in terms of x. And then evaluate, instead of doing a plus c, we're going to do half bracket, and now the bounds are going to play a role for us. Okay? If we don't see bounds, it's plus c. If we do see bounds, we're going to do this half bracket evaluation. Okay, upper bound gets evaluated first. Minus, it's always upper bound minus lower bound. Then the 1 gets inserted in for the x. Okay, we can evaluate this. We're going to go a little further. Now, on the AP exam, if this is free response, technically you could leave your answer like this and that will be fine. Okay, but for now, we're just going to go all the way down. See if we can simplify it further. So 2 squared minus 2, that's 4 minus 2, which is 2. 2 to the 4th is 16. So I have 16 over 4 minus, this is negative 1 to the 4th, which is 1. So it's just minus 1/4, which ends up being 15 over 4. All right, any questions with method 1? The second method is, rather than bringing the u back in terms of x, we'll leave it in terms of u, and then force the bounds to be variable u, and then we can use the variable u for the bounds to plug in and still get the same answer. So method 1 is everything in terms of x. Method 2 is everything in terms of u. So we're not going to convert this back in terms of x. We're going to force the bounds to change variable. So the way we force the bounds to change variable, we're going to use this assigned expression between u and x. So our lower bound was x equals 1. So if x equals 1, then u is going to be 1 squared minus 2. So the new adapted lower bound in terms of u is negative 1. And then my upper bound right now is in terms of x equals 2. I want to get in terms of u so I can match the variables here. So if x equals 2, my u value, again, this is my conversion rate, is 2 squared minus 2 in for x, so 2 squared minus 2, which is still 2. Okay, so the conversion changed, did not really change that value, but it is the adapted u value now. So I have my antiderivative in terms of u. I have my bounds in terms of u. So I'm just going to do this. Sorry, 2 above. Upper bound first, 2 in for u. then the lower bound. We end up with 16 over 4 minus the negative 1 to the fourth is just 1. So it's minus 1/4. Okay, we get the same answer either way. So I understand this is the method that most students will prefer. It just feels more straightforward, everything in terms of x. But we also need to be familiar with this as well. Everything in terms of u. Now, having said that, I see some students making a mistake and choosing a method that is not acceptable. And that is where I see students do this. They would take this form and then use the bounds here. What's wrong with using the 1/4 u to the fourth and then plugging in the 1 and 2? Why is this not an option? Yeah, these are not the same variables, right? This is in terms of u, that's in terms of x. You gotta at least get the variables to match before you can plug something in. So either you bring the u in terms of x and then use the original bounds, or if you want to use this form, then adjust the bounds using the conversion rate before you plug in the upper and lower bound. Okay, so just before you plug in, just if you went through u substitution, make sure that you're convinced the variables are the same before you start plugging in. Right, I'm going to save example 2 for later. The other big topic that we need to be able to do is even and odd functions. So let's see if I can go through that on page 10. The top is just review. We'll do that later. Let's go to even and odd rules here. So first, starting off with even. An even function is one where you see a mirror image on both sides of the y-axis. So a graph that looks something like this. It says that as long, if it's a true even function, as long as I'm the same distance away from the origin, the area on both sides are the same. So if this is 2, this is also 2. If this is 4, this is also 4. So the idea is that the entire region from -a to a is equal to if I just took half that region and then doubling it. So whatever you create on one side of the y-axis, you can create the exact same graph on the other side if it's an even function. Okay. If it's an odd function, you're going to get equal but opposite on both sides of the y-axis. So here's an example of an odd function. A graph that may look like this. Let's say from -a to 0, there is an area of 4. Then the area from 0 to a, or the definite integral, will be -4. And if I were to add the values on either side, as long as I'm the same distance away from the y-axis, it'll always zero out. Okay. Whatever I have on one side, I will have equal but opposite on the other side. Okay, let's talk about strategy for finding these information here. Okay, it's going to require us to sketch portions of the graph. And here's the order that I want us to do it in. Okay. First step is you're going to graph the shorter interval. Not the smaller area, but the shorter interval. The second step, you're going to fill out the other side. Based off of the shorter interval. So what I mean by that is if it's an even function, you're going to create a mirror image on the other side of the graph. If it's an odd function, you're going to create an equal but opposite on the other side of the graph. And then the third step is now you can resolve the larger interval. This is not an issue if there's no overlap, but this is important for us to follow if we have some overlapping regions between the shorter and larger interval. So this allows us to kind of have a structure to follow. So initially, it's not going to feel like a big deal. Example 3 and 4, there's no overlap. We don't have to do it in this order, but I think it's good to follow the same procedure for every problem. So example 3, suppose g of x is an even function. So we know we're going to create equal but opposite, where the integral from 0 to 3 is equal to 2, and the integral from -4 to -3 is equal to 4. Find the definite integral from -4 to 3. So once we have the graph all filled out, then we can just add up the region that we're asked to add up. Okay, which has the shorter interval? Good, this one here. Okay, the area may be larger, but we're after the smaller interval, okay? -4 to -3. Another thing to keep in mind is we should be reading from left to right. So the lower bound should be a smaller value than the upper bound. If it's not, then take the time to flip it and change the value. Okay? Because we're reading backwards. Okay, so always make sure that the bounds are in the proper order. So this is in the proper order. We're going from left to right. That 4 is really a 4. It really is a positive value because we're going from left to right. Okay. So from -4 to -3, I'm just going to create a region and call it 4. Next step, fill out the other side based off of the shorter interval. So just based off of this and the fact that it's even, what can we do on the other side? What would a mirror image look like on the other side? If I just had this to look at. There's also a region 4 between what and what? Between 3 and 4. Okay. Okay, so now let's resolve the larger interval. larger interval is from 0 to 3. That region has an area of 2. So from 0 to 3, we'll create 2. Which means that this other side is also what? It's also 2 because it's an even function. Okay. We don't necessarily want to add up all these numbers. We only want to add up the number that they're asking for. So they're asking for the integral from -4 to 3. What does that get us? Okay, example 4. Same as example 3, but now it's an odd function. So again, pick the smaller interval. Start here. Once we have the shorter interval filled out, go ahead and fill out the other side. Don't do the larger interval yet. It's an odd function now. What can we put on the other side if this is 4? What's on this side? -4. Now let's move on to the larger interval. 0 to 3 is equal to 2. Which means the empty space here should be what? -2. Now we can find the region from -4 to 3. Add these up. What do we get? This what? Equal to 4. Okay, so this example 5, we're going to see some overlapping between larger and smaller interval. So this is where following these steps is going to be important for us. Okay, we're back to even functions. 3 to 6 versus -6 to 3. Which one do we want to start with? Not because that's a smaller number, right? But because this is a shorter interval. We're looking at the shorter interval here. Okay, let's do that. These are both in order. That's good. Okay. What can we do on the other side if we know that this is 7? The other side we can show show what? 7 as well, okay? Just make everything symmetrical. Now, this is where it's important to have these established. I want you guys to understand that these are set in stone, okay? We're not going to create any new regions in these this is set, okay? Now, -6 to 3 is equal to 12. That's overlapping with what we already have. So what I want us to do is you can just put to the side that this is equal to 12, but we don't want to do a big overarching region to show that's 12, because then you're adding something on top of the 7, and then this is no longer true. So we just know that the region that is confirmed versus the region unconfirmed needs to add up to be 12. That's what this is saying to us. So if this is 7, what needs to be in the remaining slots if we need this region to add up to be 12? Yeah, it needs to add up to be 5, right? Because 7 plus 5 is equal to 12. But then I need to split 5 evenly on both sides. So like you guys said, 2.5, 2.5. So now we're going to add up the regions from 0 to 6. 7 plus 2.5 is 9.5. So let me just show you real quickly what a lot of students do with this problem. They would say 7 here. They would say 7 here. But then they would do this. They would say, okay, -6 to 3 is 12. So they would do this, and they will call this 12. But then what you're doing is you're adding this space above 7, and it's no longer true, right? Now this becomes really confusing because you don't know, wait, what do I do with this 12? This is overlapping with 7. So just keep reminding yourself that you're not going to step on the region that's already filled out. You're just trying to fill out the parts that's unresolved yet. Now, for homework, I would like for you guys to go back and finish in your review packets, or your homework packet, pages 1 through 4. This is the topics that we covered last week. So pages 1 through 4. Come up and get your phones. If you don't have the homework packet, you guys can pick one up. But I'll send you guys a reminder this afternoon, and also a link to the homework as well. All right, come get your phones. Many of you guys already have this homework packet. Just time tomorrow. Okay, yeah. So you do before school, lunch, or not after school. You do before school or lunch.
Yeah, but
Yeah, sounds good.
yeah.
I really thought, like, when I saw these, I was like, it's not space. Like, he was nice.